Alright, hello guys. Let's take a look at section 10.1 here, which is going to be our introduction to solving linear equations. And we're going to do that first with models and having like some sort of image to look at. So we're going to be able to solve linear equations with rational number coefficients and solve linear equations by using the distributive property and then collecting like terms. Okay, so solving linear equations is a way to solve problems in the real world. And sometimes creating a model of a problem can help you break the problem down into parts that you can visualize. So let's take a look here. This is like an old-fashioned scale. You want to measure things or, kind of see which side's heavier or if they are equal or whatnot. So some small, lightweight plastic bags contain an equal number of centimeter cubes. They're placed on a scale with some additional cubes. Okay, so just to make sure we're clear on what they're doing here, the bags are these two, okay? And then the little centimeter cubes are just the cubes. Okay, so if the scale is balanced, how many cubes must be in each bag? So let's just kind of think about that. If both sides of the scale are the same or equal, right? If it's balanced, how many cubes would be in each bag? Okay, so one way to think about it is kind of to take a look and see how there's 3 cubes outside the bags. That would kind of equally balance out those 3, right? So I know that in the 2 bags, the 2 yellow highlighted bags, we must have an equal amount of cubes, and there are 4 cubes remaining. So it kind of seems to reason that there should be 2 in each bag. Again, the green highlighted ones, their weights would obviously balance each other out. And then, of course, if we had, like I said, the 4 cubes left and there are 2 bags, there must be 2 in each bag. Okay, so let's see. Can we write ourselves an equation that represents this diagram? We're going to let x, here's the key, we have to know what the variable is representing. X is the number of cubes in a bag. Okay, so since there's 2 bags, and they're saying each bag has x cubes, this side would be written as 2 times whatever x is. Okay, so let's pretend we're pretending like we don't know how many cubes are in a bag, plus the 3 cubes down here must equal the number of cubes on the other side of the equation over here, and as a total there are 7 over there. Okay, so we really just solved that equation when we got the answer up here, and we didn't even really know we were solving an algebraic equation. We were just doing it with a model. Okay, so one way to solve the problems involves removing equal amounts from both sides and then regrouping. That's kind of what we did. So the diagrams below illustrate this process. Okay, so if we think about in the first diagram is just the original problem. Okay, so this is just the original setup right here. Sorry, it's a little sloppy there. And then you can kind of see what's going on in the, if that's step 1. In step 2, they're kind of just removing 3 blocks from each side. Okay, and if it's an even amount, then that should keep things in balance, right? If you take 3 blocks off the left side and 3 blocks off the right side, the scale should still be balanced, okay? And then just like we said, once you remove those 3, right, we ended up having these 4 blocks remaining, and so those blocks could evenly be divided up 2 and 2 to go into the bags. Okay, so based on doing it with this method, how many cubes are in each bag? Same as we got before. Okay, this just gives you a way to visualize it. There are 2 in each bag. All right, can we model each of the following problems, okay, on the next page, using bags and cubes, and then determine how many cubes are in a bag? We'll record our work using a diagram, and we're going to write an equation for the original problem, okay, and then we'll go through step by step and see if we can solve it. All right, so part A here. If 3 bags are on one side of the scale, okay, so let's draw 3 bags, 3 of the big bags. 1, 2, 3 bags. And 12 cubes are on the other side. Okay, 12 little cubes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And 12 cubes are on the other side. How many cubes must be in each bag to maintain the balance? Okay, so let's think about that. So again, we're going to say x is the number of cubes that fit in a bag. So how many, or let's write our equation first actually. Since we have 3 bags over here, right, and each bag holds x cubes, we know that 3 times whatever x is needs to equal 12 because there are 12 cubes on the other side. Okay, if we were to solve that equation, okay, we can kind of see that in this first bag, those 4 cubes could fit. In the second bag, those 4 could fit. And in the third bag, those 4 would fit. So each of these bags would need to have 4 cubes in them. Okay, so in this case, for this equation, if we were to solve that, x would equal 12. Okay, hopefully you can just visualize that, right? The equation right here is saying 3 times some value. So 3 times x equals 12. And we know that 3 times 4 equals 12. So that seems to fit. All right, let's set up another one in part B. Okay, if 3 bags and 10 cubes are on one side. Okay, so let's draw that out. 3 bags, so we got 3 big bags, and then 10 cubes. We'll try and draw those a little smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 3 bags and 10 cubes, right, are on one side, and then 16 cubes are on the other side. 16 cubes over here. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Our problem is how many cubes must be in each bag. Okay, so let's write the equation first, and then we'll see if we can look at the model how to solve it. Okay, so again, we're going to say x, our variable, is the number of cubes in each bag. Okay, so how many cubes fit in a bag? And then our equation would be, since we have 3 bags, each one holds x, so 3 times x, plus the 10 that we already have there. Okay, that side of the scale must equal this side of the scale, which had 16 cubes, right? So let's see if we were going to solve this. Okay, if we think about taking away an equal number, right? If I want to take away, this side has 10 cubes, so I can take away 10 here. 4, 8, 9, 10. Okay, so it looks like there would be 6 left over there. Okay, and really, in the algebraic equation, the step we would do here is we would subtract 10 from both sides. Okay, as you can see visually. So we would be left with, since this plus 10 and we subtract it right off, those kind of just cancel each other out. We would be left with 3 times x equals 6. Okay, which is what we're showing in our equation, right? Here's the 3 times x, because we don't know how many are in each bag, but there are 3 bags. And then we have the 1, 2, 3, 4, 5, 6 over here. Okay, and you're thinking to yourself, all right, 3 times what equals 6? Okay, we should know the answer is 2, but what you can do, just like we can subtract 10 from both sides of an equation, we can divide both sides of an equation by 3. Okay, and the reason that's going to help us is that 3 divided by 3 is just 1, so this turns into just 1x. And then on the other side, 6 divided by 3, of course, is our answer. X would equal 2. Okay, so each of these bags would have 2 blocks. There'd be 1, 2, 3, 4, 5, and 6. Okay, so that's kind of visual, and also seeing it doing the algebraic steps on how to solve a linear equation. All right, here's a similar equation worked out showing each of the steps. You see the original equation in example A is 3x plus 4 equals 7. And what they're doing is they're doing inverse operations, okay, which is exactly what we did. When you do the same thing to both sides of an equation and you're trying to solve for x, okay, like in this problem, we are trying to solve for this x right here. Okay, so the first thing we would do is subtract 4 from both sides. Okay, personally, I tend to write my equations more like the math tip over here shows, where we do them vertically. Okay, where if this was your original problem, Okay, we could subtract 4 from both sides. Okay, and again, what that's going to do for us, that's going to get rid of this plus 4 that's sitting there. Okay, and we would just get down to this step where once we subtract 4 from both sides, we would have the 3x equals 3. And then just like the previous one that we did, we could divide both sides by 3 and get x equals 1. Okay, so let's solve a couple. Let's do a few examples and see how this works. Okay, so we'll use inverse operations, and we'll go ahead and solve a couple of these here. So just to give myself some space, I like to solve them vertically. 2x plus 0.4 equals 18. Okay, so again, our goal is to figure out what x equals. We want to solve this thing for x. So what we want to do is go ahead and do everything, or get rid of everything else in the equation, okay, using inverse operations. So if we see an equation as 2x plus 0.4, the inverse of adding is subtracting. So the first thing we would do is subtract the 0.4, and we're going to do that to both sides of the equation, okay? And that's why we're allowed to do it, right? Think of that scale. If you subtract some amount of cubes, you need to do it to both sides to keep the equation equal, right? Because these are equations. There's an equal sign there. Okay, and then what that gets us, the plus 0.04, when we subtract it off, just cancels that out. And we are left with just 2x. And then 18 take away 0.4 is going to be 17.6. Okay, you always want to do the adding and subtracting first. If you think about the order of operations, right, parentheses, let me just write this out. Remember, parentheses, exponents, multiply and division, add and subtract. Remember the please excuse my dear Aunt Sally little saying. That's when you're evaluating things. But when you're solving and we're using inverse operations, you actually generally go in the opposite order. So you want to take care of any adding and subtracting first. And now at this point, we're ready to undo any multiplying or dividing. Okay? So in this case, we have, in our equation right here, we have 2 times x equals something. So to get rid of multiplying by 2, the inverse is to divide by 2. So we're going to divide both sides by 2, okay? And that will allow us to get our answer. Okay, and when we do that, again, the multiplying by 2, dividing by 2, those are inverses, they cancel out. So we will get an answer of x equals 8.8. Okay, we solved an equation. All right, why don't we do a couple other examples? Why don't we do example B? Okay, let's get some space here. They don't give us a ton of room here, did they? Oops, there we go. All right, so example B, we have negative 1/3 x minus 4 equals 12. Okay, so what we want to do here is same kind of thing. Let's just rewrite the original and give us some space here. Negative 1/3 times x minus 4 equals 12. Okay, so again, order of operations in reverse says we will add 4 to both sides first. Okay, our goal here, remember, is to get this x by itself. Okay, the fancy word is isolate, right? Isolate the variable, get it by itself. So by adding the 4 to both sides, we will get negative 1/3 x. Okay, this minus 4 got canceled out by the plus 4. And then, of course, 12 plus 4 is 16. Okay, so now this is a little tricky because it's multiplying by a fraction. So we can divide both sides by negative 1/3. Okay, remember, since it was multiplication originally, the inverse of that is to divide. So when we divide by negative 1/3, it's going to cancel out the multiplying by negative 1/3, and we'll have just x. So the issue becomes, how do we do 16 divided by a fraction? Okay, if you remember, to divide by a fraction, you're going to multiply by the reciprocal. So we're going to take our 16 and we're going to multiply by it. So the reciprocal of this guy means to flip the fraction. It would be negative 3 over 1. Okay, and to multiply a whole number by a fraction, okay, it might help to put a 1 under there. Now, in this case, since both denominators are 1, it wasn't really necessary, but we're just going to multiply straight across. So the 16 times the negative 3 will get us our answer of negative 48. And again, it's just a 1 in the denominator, so that doesn't impact anything. Okay, why don't we do one last one real quick? Let's just jump down and do part E just for fun. So part E says 14 equals 3x minus 2. Okay, so they just switched the side, the variables on the right side here. That's okay. We're going to do the same thing. So we're going to add the 2 first to get rid of that. Do it to both sides of the equation. Keep things equal. Right? 14 plus 2, of course, is 16. The 3x minus 2, since we added 2, those cancel out, and this will just equal 3x. And now we have 3 times x equals 16, right? So 3 times something equals 16. We can get rid of that multiplying by 3 by doing its inverse, which is division. Okay, the 3 dividing by 3 cancel out. So in this case, our value of x, we can just leave it improper fraction. There's nothing wrong with that unless they say not to use them. But we could write that as 16 over 3. All right, let's move along here. Let's take a look. Here's another equation, number 7 here. Can we use the properties of operations, okay, or other explanations to describe each step? So there's actually a couple properties that were kind of hidden over here in the book. And we talked about this distributive property a little bit, but here it is technically, and I'll show you an example of it as well. But basically, if you have something like, I want to highlight, if you have something like A times B plus C, what you can do, you notice they tell you it equals A times B plus A times C. You actually multiply the A times the B and times the C. Okay, and let's just show what's really going on. So let me write it a little bit bigger, just so we can see that it's true. A times B plus A times C. So what it's saying, for example, and let me just make one up with some numbers. Let's say it is like 3 times 4 plus 5 or something, right? Just to give it some numbers. Okay, the property is saying is that it would equal 3 times the 4 plus 3 times the 5. And sometimes we draw those little arrows there just to remind us that we're multiplying each of those. And if we think about that, since it's numbers, we can actually do the multiplication, right? 3 times 4, of course, is 12. 3 times 5 is 15. Okay, and 12 plus 15 is 27. Okay, here's how we can show that that's true. Okay, take a look at just this original expression right here, right? We know that to do the order of operations would say do the 4 plus 5 first. Okay, so just to show this step, 3 times, so 4 plus 5 is 9, right? And what is 3 times 9? It's 27. Okay, so it worked. Okay, it definitely worked. So here's where that can be used in solving equations. If we take a look back at this example 7 here, the original equation was 3 times and then x minus 2 equals 8. So the next step would be to actually distribute that 3, okay, or multiply it by each of those, and you get the 3x, and then minus 3 times 2, which is 6. So this first step was based on the distributive property that we just saw. Okay. From there, they just go ahead and solve the equation. Okay, this is now the problem they're solving. So you see some of the other steps, they are just using inverse operations. Okay, adding 6 to both sides, like we did several examples of just a few minutes ago. A set of parentheses. Okay, when it's something, you know, let me highlight this again. So when it's some value times a quantity in parentheses, that's when you would use that distributive property. If we don't see that, then it doesn't matter. And one of the places where it did show, remember in the previous sections when we were trying to find the pattern or find an expression for a pattern, and it ended up being like something like the first term, let's say it was 4 plus 5 times n minus 1 or something like that. That's where we were actually using the distributive property. If you wanted to simplify it, you could multiply that 5 by each of those. And then you could then collect the like terms, okay? Meaning combine the 4 and the minus 5 because they're both just whole numbers to be a negative 1 plus 5n. Okay, so that may show up in some problems as well. That's the old distributive property. It gets used quite a bit. And then using inverse operations, we can solve equations. Okay, now again, this one here that I'm just doing, this was not an equation. There was no equal sign in there. It was just using the distributive property in a different way. All right, so hopefully it helps. Little intro on using models to solve linear equations, and then the distributive property as well. All right. All right, so the distributive property is something that just shows up in certain problems, and you know you're going to be using it when you